Hi, this is Mrs. Wolf. So what I want you guys to work on today is your atomic theory timeline. And the point of doing this, in addition to the timeline that you've already done, is so that you have really the short and sweet story. And I'm going to show you some tips and tricks to help you memorize this. So for your quiz, you are allowed to use your timeline, but for your tests in chemistry that are coming up, you're going to have 2 chemistry tests. You're going to have to memorize all of these scientists in the timeline. So I want to give you some ways that are going to help you memorize all of these scientists and what they did and what their contribution was to the atomic theory. So the atomic theory, what you're going to do with this paper, first you're going to fold it in half. And the atomic theory is really the history of what we've thought the atom has looked like over time. So as technology has evolved and science has gotten even better, our idea of what the atom has looked like has changed from back in 400 BC to what we think the atom looks like today. So what I want you to do with the timeline, just fold it in half first. And then we have 1, 2, 3, 4, 5, 6, 7 scientists. So I'm going to open it up and I'm going to split it into 7 sections. Let's see, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All right, so you have 7 sections there. And we want to put the scientists' names on the inside since you see that there's no names on the outside here. Actually, let me put my name, so in case this gets lost. Okay, so 400 BC. This picture here is a picture of Democritus. So we're going to write Democritus. Then the next picture is Aristotle. So Democritus and Aristotle are the first 2 names that you need to memorize. After that, there's actually a little song that I'm going to link in the bottom of this agenda for today in Google Classroom to help you memorize the names of everybody else. I actually sing that song in my head to remember, I think all the science teachers do, to remember the order of all of these scientists. So Dalton comes next. I'm going to have you pause the video and listen to that song, or maybe listen to the song after you've watched this timeline video to help you remember the order of those scientists. So Dalton, whoops, the lights are off there. Sorry, if you sit in here too long without moving too much, the lights are going to turn off. So Dalton, Thomson, Dalton, Thomson, Rutherford, Bohr, Schrodinger and Heisenberg, and many, many more is how the song goes. So I'm just gonna write Schrodinger. So we'll get there, but this last group of modern scientists, it was more than just Schrodinger, Heisenberg, Einstein. There are other scientists that contributed to what they thought or what we do think the atom looks like currently. All right, let's go back to Democritus. So Democritus, 400 BC. He was a philosopher, and what he really did, he didn't really have any technology that helped him in deciding or hypothesizing what the atom looked like. So really, what a philosopher does is they pretty much sit around and think, what is the atom? What could it potentially look like? And he used the word, so let's write this down. Everything that I'm writing here, I want you to write down. He used the word atomos, which means not to be cut. So he thought that the atom could not be cut into anything smaller, that the atomos, or the atom, was the smallest piece of matter, really. Atoms are made up of a single material. So like I said, cannot get any smaller. We knew nothing about protons, neutrons, and electrons. And he thought that the atom, we're going to draw a picture. I'll leave space down here on the bottom for the pictures of what we thought the atoms look like. And he thought they were random shapes, really had no idea. So I'm just going to draw squares, circles, triangles. So the atom are all these different shapes and sizes. Different shapes and sizes. So that's going to sum up Democritus's theory of what the atom looked like in 400 BC. Okay, after that, we're looking at 300 BC. So here's our picture of Aristotle. Aristotle, again, was a philosopher. He had a very different idea of what the atom looked like. He thought the atom, or all matter, was made up of these four things. Fire, fire, water, air, and earth. Very different idea from what Democritus had thought the atom looked like. So Aristotle said, no, I don't think anything about these atoms. So he really was not following Democritus's idea at all. Aristotle had his own idea that everything, all matter, must be made up of these four components: fire, air, water, earth. So for about 2,000 years, we really had no advances in what we thought the building blocks of matter are. So we really stuck with Aristotle's idea, and you might hear the death of chemistry for 2,000 years. So there's 2,000 years that pass by without making any advances in the idea of what the atom looks like, in the atomic theory. Okay, our next scientist we're looking at, this guy, 1803, this is Dalton. One of the words I want you to think of when you think of Dalton is going to be uncuttable. So this was his catchphrase, I guess, or the word that I want you to think of when you think of Dalton, uncuttable. He said that all matter is made up of atoms, and all of those atoms are uncuttable. So again, he's actually kind of agreeing with Democritus, if we go back to Democritus's ideas, that, where did he say? That atoms cannot be cut. So Dalton is agreeing with Democritus. Yes, I think that atoms are uncuttable. Just want to make sure those lights don't turn off on us. Okay, Dalton says atoms are uncuttable. Atoms are of the same element. So same element, same elements are exactly alike. So if we have oxygen atoms, all oxygen atoms are going to look the same, or all hydrogen atoms are going to look the same. So let's just draw a ball. He believed the atom was this solid sphere, nothing inside. We knew nothing again. Still up to this point in 1803, we still don't know anything about protons, neutrons, and electrons. And if you want to draw a picture that goes along with Aristotle, I guess you can draw water, not really an artist here, fire, earth, draw some sort of earth, and air. All right, so just so you have a picture. I don't know, whatever you want to do there. All right, back to Dalton. We got our uncuttable atoms, solid sphere, same elements, look exactly the same. All right, so that's in 1803. Let's move on to Thomson. I'm going to put J.J. Thomson here, and the reason that I put J.J. is because when I see J.J., I think of plum pudding. Plum pudding is the model that J.J. Thomson, so you see P.P. for plum pudding, J.J. for J.J. Thomson. J.J. Thomson's idea of what the atom looked like resembles something like plum pudding. And what we think of, I guess, more as Americans, I think plum pudding is a European kind of food. We want to think of like a chocolate chip cookie. So what he thought the atom looked like, he thought that the atom is this big, positively charged blob of material with negatives throughout. So science has actually advanced a little bit for J.J. Thomson once it got to 1897 when Thomson was doing his research. And he started to find that there must be charged particles within this blob. So Dalton thought it was this solid sphere, nothing inside. So we're making an advance here, so it's changing just a little bit. You'll see as the pictures go on that we add a little bit more and a little bit more to our picture. So J.J. Thomson has this big positive material with all these negatives scattered throughout it, these charged negative particles. Let's see. So our plum pudding model, small negative charged particles inside an atom. And we started to name those little particles have names, which we know as electrons. So let's write positive material with negatives throughout. So just trying to bullet point the important stuff here. So that was really J.J. Thomson's contribution as, like I said, as science advances, we were able to determine or hypothesize that there are charged particles within that atom, what we know to be the atom. All right, let's move on to Rutherford. Rutherford is 1908. So we're now in the 1900s. And what Rutherford's contribution to the atom, he is moving off of and advancing past J.J. Thomson's idea. Electrons are scattered around a nucleus. So not only do we have this big blob of positive material with negatives scattered throughout, but Rutherford's experiments led him to believe that there was more of a positive dense center. So let's put that down. Positive dense nucleus, not just center, nucleus. He also, from his experimentation, decided that there was a lot of empty space, which we are still believing is true, that there's a lot of empty space in an atom. And that the electrons are scattered around the nucleus. So I'm going to draw the negatives just on the outside of this positive. So these are all my electrons. And they are scattered randomly. We don't really know anything about paths or clouds or any of those things that we're going to see later on. But we have a positive dense nucleus with negatives just randomly scattered throughout was Rutherford's idea of what the atom looked like. All right, let's move on to Bohr. So we're really familiar with Bohr after we did those paper plate models, and any students in any other classes hopefully did some other model. I'm sure you did some other model, not necessarily with paper plates, but Bohr models are the ones that we still draw today because Bohr models are nice and neat. We have those defined paths, which we'll see as we draw the picture down here. So Bohr's contribution. Let's see, I'm just going to read off of your timeline that you already did. So most of the atom's mass is in the nucleus. Electrons travel in paths. That's the key here from Bohr, Bohr's contribution to this whole atomic theory. So electrons travel in paths. Energy levels, what else do we call them? Shells, rings, any of those words, paths. Most of the atom's mass is in the nucleus. Okay, I think that's really Bohr's focus. That's what I'm going to limit it down to because I know your timeline has even more information, but I'm trying to even simplify that more for you. So now we have our nucleus, where we have pluses and we have neutrons, which we still believe to be true. So we actually kind of skipped a scientist in here. There's a scientist by the name of Chadwick, and there's tons of other scientists that actually aren't included in this particular timeline, who haven't gotten credit for their contributions to the atomic theory. But there was a scientist in here between Rutherford and Bohr that experimented as science has advanced and determined that there are neutrally charged, well, I guess not charged, neutral, not charged, neutrons in the nucleus in addition to those protons. So positive dense center for Rutherford, and then between 1908 and Bohr was 1913, we have come to believe that there are positive protons and neutrons in the nucleus. So you want to make sure you have protons and neutrons in the nucleus here. Okay, and then Bohr said that there are rings or defined paths that the electrons are going to travel on. And we know, since we've been drawing Bohr models, that on that first ring we can only hold a maximum of 2 electrons there. All right, moving on to our modern day scientists, Schrödinger, Heisenberg, Einstein, and all of the scientists that have contributed to our current model. Let's see. Electrons are found in electron clouds. Electron clouds. So clouds are the key word here. Electrons move around the nucleus billions of times a second. Electrons are located, or electron locations depend upon how much energy they have. So I'm just going to limit it down to there are electron clouds. So very similar to Bohr's model in 1913. the advances that we've made up to today, we still believe there are protons and neutrons in the nucleus, positive dense center. But we have come to believe, and it's really hard to draw, so I kind of just make it a wavy line, but we don't believe the electrons are traveling in these defined little paths like a train on a track, but instead we believe that electrons are found in these large regions. And they're not just traveling in a circle, they're actually traveling in all directions, and it's kind of hard to show on this video here, but in all directions, three-dimensionally, whipping around billions of times a second around that nucleus. So I think on your quiz or your test, when you're asked to draw what these clouds look like, just kind of make the lines a little bit wavy, or some students like to use their pencil and then smudge it to show that there's a cloud or a region around the outside of the nucleus where the electrons can be found. All right, so I would highly recommend holding on to this, of course. You have really the bulleted points of what each of the scientists have contributed. I like this picture because you get to see how the atom has changed over time, or what our idea of the atom is and how that's evolved. And I like that just a little bit has changed each time as we build and build and build. And who knows, maybe 20, 30 years from now, whatever it may be, there might be a new column of what we think the atom looks like. And this could definitely change as science gets better. All right, so watch that video. Make sure we memorize the names. There's that awesome song, Dalton, Thomson, Rutherford and Bohr, Schrodinger and Heisenberg, and many, many more. So when you listen to that, hopefully that song will get stuck in your head. Again, I'll link that in your Google Classroom for today. That's it. So the next thing you're working on, just take a look at the agenda so you know what to do after you finish your timeline. This is for you to hold on to, put it in your binder, study it. All of the chem tests that are coming up in the future are going to have the atomic theory. You're going to be tested on that atomic theory. All right, hopefully that helped.